Good morning, everyone. So, in the last class, we studied about the basics of MOS transistor. We saw how to explain the operation of an MOS transistor using energy band diagrams. Then we saw the characteristics of the MOS transistor, the ideal of an ideal transistor. In today's class, what we are going to see is that we will look at what happens if you scale the transistor, that is, if you make the transistor smaller and smaller, as well as some of the advanced devices which are currently in the market. First of all, okay, let's start with something known as the body effect. Okay, body effect. So we saw that in a symbol model. Okay, in the last class we talked about the symbol equivalent circuits of the MOS transistor. One of the simplest models is, okay, you can assume like that there is no current flowing through the device when the gate voltage is lower than smaller than the threshold voltage. The threshold voltage, okay, but it depends on a lot of things. Okay, first of all, we saw that the threshold voltage depends upon the doping. Okay, for example, if you look at the simple expression, the doping comes into the threshold voltage using this expression. But if you look at the third term in this threshold voltage expression, this is nothing but the depletion charge. So this is a depletion charge which is being supported by the gate. But this depletion charge also depends upon the substrate bias. Okay, it's similar to a PN junction. Okay, if you vary the substrate bias, for example, if you draw a transistor like this one, okay, we saw the depletion region is somewhere like. So this extent of the depletion region will depend upon the substrate bias. So any change in the supply substrate bias, okay, that modulates this depletion charge. Okay, that in turn modulates the threshold voltage. So just like in any reverse bias PN junction, so we need to add the substrate bias inside this under root expression. So this expression, we can make it much more simpler. What we are going to do is that we are going to add and subtract this term. Okay, so we add this term and we are going to subtract this term. Why we are going to do this thing? It will become clear. That is because if you add this term, it is nothing but the threshold voltage without any substrate bias. So you can call it as VT naught. That is the threshold voltage in the absence of any substrate bias. So then we can write the threshold voltage as a function of the substrate bias. So that is nothing but the VT naught plus this quantity. So this quantity is nothing but you take the under root the constant terms out, then only the under root 2 phi f plus VSB, that is substrate bias with reference to the gate source voltage minus the 2. So this is, so you can write the threshold voltage at for any substrate bias in terms of the threshold voltage at no bias plus some factor. This factor is known as a body effect parameter. This body effect parameter. So you can see this the body effect parameter is nothing but this prefactor here. This depends upon the substrate doping as well as COX. For example, if the substrate doping is very large, okay, that means the sensitivity to the substrate bias is very large, and that is same thing with so and also COX. Okay, COX is, okay, if you recall, is epsilon ox by T ox. So for thicker oxides, thicker gate oxide also, the substrate sensitivity is very large, and the sensitivity goes down if you scale the gate oxide thickness. Okay, so this is an issue for if you are working with a deeply scaled MOSFET where the gate oxide thickness is very small. So if you look at, if you in the case of n channel MOSFET, what we are going to do is that suppose if you the substrate bias, if you apply negative bias, if you are applying more and more negative bias, okay, so this is n plus here, this is n plus here, this is P, okay, right. So so you can see, right, this junction has to be reverse bias. Okay, it should not go into turn on mode. Okay, the substrate to source or substrate to drain junction, it should not turn on because they are all PN junctions. So what you can do is that, okay, you can apply maybe small forward bias, okay, small forward bias, and you can apply large negative bias, reverse bias. There are some circuit companies, there are some design companies which may apply a small forward bias. I will come to that, why do they do that. but in more or less cases, we are more worried about what happens when you apply large negative bias. Okay, when you apply large negative bias, what happens is that the VT of the transistor is going to increase in the case of N-channel devices. Similarly, in the case of a PMOS device, okay, if you apply large positive bias at the substrate, the VT of the transistor, the mode VT, okay, I am talking about mode VTP, is going to increase. So, the threshold voltage becomes a function of substrate bias. So, earlier I mentioned about you can still apply some positive bias voltage, you can slightly forward bias the junction, okay, you do not go into much. The advantage is that, okay, so you can reduce the VT, okay. In the same way you apply, when you apply negative bias, your VT increases. Similarly, when you apply small positive bias, okay, so that bias has to be less than something like 0.6 volts, because you do not want to turn on the junction. If you apply small positive bias, you can reduce the VT, you can reduce the VT. So, if you reduce the VT, what happens is that your current will increase, okay. So, there are some circuit design companies which utilizes this principle. So, you apply something known as an adaptive body bias, you apply a small forward bias so that you can speed up the transistor. And similarly, you can apply a negative bias, that is, you increase the VT of the transistor, that will allow them to reduce the off current. So, that is all about intentionally applying a substrate bias, okay. But there are some circuit topologies where it comes naturally, okay. Even if you do not apply a specific bias, okay, by virtue of the fact that how you hook up the different NMOS or the different PMOS, okay, there is an intrinsic body effect happening here. For example, if you might have studied in the digital integrated circuits, okay, so you have these universal gates NAND and NOR, okay, those are universal gates because you can realize all type of logic Boolean expressions using just NAND and NOR gates. For example, a 2-input NAND gate, it looks something like this one, okay. So, that it is an extension of your NOT gate, okay, the CMOS NOT gate, but the NOT gate has only one input, but the NAND gate you have more than one input. For example, in the NAND gate, it looks like something like this one. Yeah, there are two transistors or two NMOS transistors, they are in series, okay. These are known as the pull down configuration. In the pull down, so there are two NMOS transistors in series, okay, it is connected to ground here, the output is taken at here, and it is connected to the supply voltage through a parallel combination of two PMOS transistors, okay. This is NMOS. So, the function is the output is equal to A dot B complement. So, this is a NAND expression. Similarly, you can construct NOR gate also. The only thing is that in the NAND gate the NMOSs are in series, but in the NOR gate the NMOSs the PMOSs are in series, and the NMOSs are in parallel. Okay, so F is equal to A plus B dot complement. So, if you look at here, okay, so why we are so this the body effect, the effect of that body effect comes here. That is because, so normally what happens in the NMOS transistors, you may connect to a substrate voltage. So, if you are not applying any voltage, if you are not interested in applying any voltage, what you normally do is that you may connect all the transistor wells, okay, you connect it to ground. Suppose you connect it to ground here, you connect it to ground here, right. Similarly, you connect it to ground here, this connected to ground here. So, and similarly for the PMOS devices, okay, for the PMOS devices you connect this thing to the VDD, this thing to the VDD, this thing to the VDD, this to the VDD. So, there is something interesting happening here. For this transistor, for the B transistor, okay, B transistor, so this is the VSB is equal to 0, VSB is equal to 0. But for this transistor, your source potential, the potential at this node is always higher than going to be at the ground. Okay, so there will be a net VSB here. Okay, there is a net VSB here. This was not intended. Okay, this was not intended. So you can see the VT of this transistor and this VT of this transistor could be different by virtue of the fact that there is this VSB coming here. Okay, so this is known as a stack effect. Okay, so this is known as a stack effect in the NAND or the NOR topology. So, but for the PMOS devices it won't happen because they are in parallel here, and both of them are connected to VDD. Okay, so there is no body effect coming in the PMOS devices, but it will come for the PMOS devices in the NOR topology. Okay, in the NOR topology, because the PMOSs are in series. Okay, so then you will see the body effect happening for this transistor. Okay, which are not connected to the VDD, which is not close to the VDD. So you can see that the VT of this transistor and the VT of the transistor, they are different while operating this device. Otherwise, if you take out this device, if you have the ability to separate these transistors and measure the individual VTs, they may look similar. Okay, but when sitting in that configuration, okay, the way you have put the transistors in an order, so that is what is modulating that VT of this transistor. So you have to always keep in mind about the stack effect while designing the digital circuits. So far I didn't mention anything about the physical. Okay, what does the physical structure of the transistor looks like? Okay, so we explained using a band diagram. So what all you need to record is, so there is an N plus, this is an N plus source and drain, there is a gate here, as a substrate here. But the actual the transistor, okay, it look different. And so if you just draw a transistor schematic, something like this one, okay, so this is a favorite circuit schematic, but the circuit schematic remains the same, but actually people, when you work with the transistor, the actual physical structure keep on changing. So we will see what is due to, but if you look at the transistor structure in the 80s, okay, in the early 80s, it may look something like this one. So this was, I am talking about only one transistor here. This is a source, this is a drain. So this is your gate, and this is your TOX here, and this is something known as a field oxide. Okay, this field oxide is to provide insulation. Okay, so this is to provide isolation between other transistors, because there could be another transistor in the left or the right. So if you want to isolate two transistors, the field oxide provides isolation, because you provide a thick field oxide here. So this is all about one transistor. Suppose if you are interested in CMOS, okay, that is if you look at the history, so earlier people were designing only with NMOS transistors. Okay. Then they found out that a CMOS, okay, it has very slow standby power dissipation. They started designing using CMOS devices. So the CMOS, okay, the first technology which came was a single well CMOS process. Okay, so in the CMOS you need both NMOS as well as PMOS devices. So how do you put both NMOS and the PMOS on the same chip? So because their substrate needs to be different. Okay, so one way to create is you create a separate well inside the substrate. So in this case, all the PMOS devices, okay, these are PMOS devices. These PMOS devices, they sit in something known as an N well. So you create in the fabrication flow, very early in the process itself, you create a well in the substrate. So that is this well. Then you build all the PMOS devices in an N well. Okay, there could be multiple N wells. Okay, I am not saying that all PMOS devices in an integrated circuit sits in the same well. Okay, so there could be multiple N wells, and all the NMOS devices they sits in the substrate. So then you make the transistors, and later you interconnect it. Okay, so this is the top layer interconnect. You may so for interconnecting they may use a polysilicon, okay, doped polysilicon, or maybe one or two metal lines. Okay, that was all there in the very early days. Then people moved on to other physical structures. For example, here it was a single well CMOS process. Okay, then people started talking about something known as a twin well CMOS process. Okay, twin well CMOS process. In the twin well CMOS process, each NMOS and a PMOS, they sit in their own wells. Okay, so in the case of NMOS, okay, it sits in a P well. Okay, although your substrate could be a P silicon, but still they construct their own P well. And similarly, NMOS, okay, it sits in an N well. PMOS sits in an N well. And these are so on the isolation technologies, they also have improved. Okay, so from this field oxide, okay, this technology is something known as a low-cost. Okay, so it's known as how you create this field oxide is known as local oxidation of silicon. from this low cost, okay, the people moved on into something known as STI. Okay, STI stands for shallow trench isolation. So you create trenches inside the silicon and you fill it with oxide. Okay, so that you isolate this device and this device. Okay, so for example, in a simple CMOS inverter, there is an STI which is which is separating between an NMOS and an PMOS. So there are various reasons. I don't want to go into this one. If you want, I can answer in the question and answer session. So this was a popular technology, the twin well CMOS process. Okay, in even today also all the NMOS and the PMOS they sits in the twin well technology. So this happened during 1990s to 2003. Then after 2003, people found out that okay, around 2000, okay, early 2000, the people found out that it is very difficult to make the transistor smaller and smaller at the same time with higher and higher performance. So the people came up with the different innovations, okay, different innovations, and one of the if you look at, if you buy any you don't buy transistors, right? You buy chips, right? Because the chips may contain millions or billions of transistors. So if you buy modern chips, especially microprocessors or DSPs or something like that, okay, so the modern day MOSFET comes in two variants, okay, two variants, okay, there is something known as, you might have already read somewhere, okay, there is something known as FinFET, I will come to that later. So this FinFET, so it's some kind of a three-dimensional transistor. So earlier the transistor looked like this one, okay, so these are three-dimensional representation. So the source is here, the drain is on the other side, the gate is going like this one, right? So this is a planar transistor, okay, planar FET means, okay, the current, okay, whatever the current it is flowing on this plane, okay, the sheet of electrons or these electrons are going from whether the source or the drain, the carriers are flowing from source to the drain in a plane, okay, in a plane. But in the case of FinFET, you can, okay, how do you construct this planar FET from the FinFET? Okay, so one way to, because some people in early, the students may have some confusion how to draw the FinFET. Okay, one way to remember is this one is that you make this very thin. Okay, you make this very thin and you bring it inside this gate. Okay, so you make it very thin here and you raise this silicon area. Okay, you raise the silicon area and put it inside the gate. So what happens is that the gate goes over this thin piece of silicon. Okay, so this looks like the fin of a shark. Okay, for example, you might have seen in the fishes like shark, they have something known as the dorsal fin. Okay, so that fin raises above their body. Okay, so this structure looks like the fin of a fish or a shark. That is why it is called a FinFET. So this gate, okay, so you can see the gate is on this side, the gate is on this side, and gate, okay, there is a small gate on the gate is also on the top. Okay, so it's like for this silicon, okay, the gate is there on all the three sides. So it's no longer a planar device. Okay, so people call it as a FinFET or something on some multiple gate transistor. Okay, so this is more. So this transistor has only one gate. But this transistor has got either two, depending upon how many, the way you count, either there are two main sides and one small side. Okay, it could be 2 or 3. So different companies, okay, they may have their own terms. For example, most of the companies call it as a FinFET. Intel call it as like a tri-gate device, but all of them are the same. So the FinFET, most of the companies, suppose you buy a chip from Intel or a chip from Samsung or from a Qualcomm. Okay, so most of them they are composed of FinFETs these days. And there is another variant. Okay, you can see there is if you the transition from a planar FET to a FinFET. Okay, it's a very large. Okay, process wise it is very complex. So some companies came up with a different solution. Okay, it is something known as FDSOI. So it is known as a fully depleted silicon on insulator technology. So it is mainly championed by ST Microelectronics. Okay, they are being manufactured at Samsung and Global Foundries. So there are some chips outside using FDSOI technology also. So FDSOI is similar to a planar transistor. Okay, the planar transistor, but the only difference is that the silicon thickness. Okay, so it is similar to so there is something known as an SOI technology. So SOI technology, the wafer is something like this one. Okay, so there is a top silicon, then there is again oxide. Okay, and again this is silicon. So this is how the wafer looks like. So in the case of an FDSOI technology, okay, this top silicon is very thin. Okay, so it may be less than 10 nanometer. Maybe less than 10 nanometer. So that is why. So this is an example. This is a cartoon of an FDSOI transistor. So you have a buried oxide. Okay, this is a buried oxide. Okay, this is known as box or the buried oxide, and you have the source drain here. Okay, so why we are using all these transistors is that they are electrostatics or the gate control. Okay, is much superior compared to the planar FETs. So that is why people have moved from this configuration to the FDSOI or FinFET, because they have the gate has more control on the channel. So we looked at a different, okay, so the different the different physical structures of the MOSFET. So the MOSFET, if you look at the gate length of the MOSFET, okay, in early 1970s, okay, I'm sorry, this is, okay, this should have been micron. Okay. There's a conversion. Okay. So the gate length was around 10 micron. Okay, 10 microns. That is this transistor, slide 58. Okay, if you look at this transistor, okay, so this transistor, when people earlier made, okay, it was somewhere around 10 micron device. Okay, this was 10 micron. Although it is small to human dimensions, it is something like 1/10 of a human hair. A human hair. Okay, so roughly our hair, okay, our hair is roughly around 100 microns, so it is around 1/10. Okay, and still people call it as a long channel transistor. This was around 10 microns, but these devices, okay, this could be somewhere around 15 nanometers. Okay, so this is around 15 nanometers. So if you count each and every generation, so every 2 or 3 years a new generation comes. So between 1970s to today, okay, there were roughly around 15 generations of MOSFETs. So each of these 15 generations, okay, people modified. There were some minor as well as major modifications they did to the previous generation. So the question is why they look different. Okay, why they look different is that if you make the transistor smaller and smaller, you can see from 10 micron to 15 nanometer. Okay, you are making the transistor smaller and smaller. Then what happens if you don't do careful scaling is that, okay, the transistor performance worsens. Okay, so you go from a good transistor to a worse transistor okay, you are shrink the transistor, okay, but without any benefits. Okay, all you got is a geometrical shrink, but your transistor performance is bad. Your drive current may not be good. Your off current may be large, and also your transistor may fail very easily. So you need to look at all these things. Okay, you are not only doing scaling. Okay, you are not only doing scaling for the sake of scaling. So you need to think about the performance, you need to look about the leakage power, you need to worry about the reliability, and you need to worry about something known as the manufacturability, whether you can make these transistors in very high volume. Okay, because every chip may contain millions, hundreds of millions or billions or tens of billions of transistors. So you should be able to manufacture this thing. So whatever the modifications, whatever the process changes you do, it should pass all these, it should get tick in all these areas. Okay, it should be the performance, power, reliability, and manufacturability. So why do we scale transistors? Okay, why do we scale transistors? One thing is that we saw that the current is proportional to 1 over L. So if you shrink the transistor, your drive current increases. And suppose you are switching, okay, all you are doing is that you are charging and discharging capacitors. So if you have a higher drive current, okay, for a phase, drive current is that you can charge and discharge the capacitors in faster manner. So that translates the speed of the circuit. Okay, so typically circuit designers they expect roughly 30% improvement every generation. It's very hard to make, but that was. And other thing is that when you scale the transistors, you are making it smaller and smaller. For example, this was the area. Suppose you make it smaller and smaller. So earlier, now you can put the same number of transistors in this one quarter. So you have reduced. Okay, for example, if for some applications, okay, you want only suppose you require only 10,000 transistors. So you can make the same circuit using the same 10,000 transistors in a reduced area. Right. Other thing is that, okay, you suppose if you are a circuit designer or a product designer, you are saying that I am not constrained by the area, I can still use the older area. Now what happens is that, okay, you have additional, suppose you use 10,000 transistors, you have additional 30k transistors here. So you can put it here, put it here, put it here. Okay, so you can think about, okay, what can I do with these extra transistors? So that is what happened. If you look at if your cell phones, okay, if the cell phones were introduced in early mid 80s or something. So from there to here, okay, so earlier cell phones were used to make the only purpose was to make calls. Okay, so what do we have now? Okay, you have in your cell phone you can take camera. Okay, camera, you have GPS, here. Then what? Similar. Okay, so there are a lot of things, right? You can do with your cell phone. Okay, so that comes because you have a lot of there are a lot of there is space to put a lot of transistors. Okay, so you can come up with additional functionalities. Okay, so that is why all your computers and the communication and the computing get converged into something known as a smartphone. So you can do a lot of things which you are not able to do in the earlier devices. So that comes because you have all these additional transistors, okay, additional small transistors.